Hi everybody, my name is 𝐂𝐨𝐧𝐭 and in this video we'll be discussing the next problem of April long challenge, which is the factor tree. So without further ado, let me read the problem out. The problem says that chef lives in a country called Chefland. The country can be represented as a tree of n cities numbered through 1 to n, and they'll be connected by n minus 1 roads. For each valid I, the cost of a house in city I is ai. Okay, so basically there's a value associated with each node. Okay, we should answer q queries. In each query we'll be given a city u and v. Will be given a pair of cities u and v, possibly identical. Chef is planning to buy houses in these cities. Chef's happiness quotient is equal to the product of the costs of houses in all cities which lie on the simple path between u and v. Okay, both inclusive. Since chef loves playing with factors, he is asking you to tell him the number of factors of this happiness quotient modulo 10 raised to power 9 plus 7. I hope the question is clear. You can read it out again by going to this link or simply pausing the video. The input format is that in the first line we'll be getting t, which is the number of test cases, and then n, the number of cities. Then n minus 1 lines will follow, and each line will contain two integers x and y, which means that x and y are connected by a road. The following line will contain n integers, that is representing a1 to an, then an integer q, then q lines, each having two integers u and v describing the query. So for each query we have to print the answer, which is the number of factors of product of all the costs of all the houses which lie on a simple path between u and v. Okay, so the constraints are that the number of test cases will be 1 to 3, and the number of cities and the number of queries can be up to 10 raised to power 5, and the prices can be up to 1 million. And it is also given that the sum of n overall test cases over all the 3 test cases will not exceed 100,000, right? There are different subtasks. In the subtask 1, the n and q will be less than or equal to 1000, and in the second subtask q can be up to 10 raised to power 5, but n will be less than or equals to 1000, and in the subtask 3 it will be the original constraints. So this point onwards I'll be discussing the solution, so it will be a good time to pause and think about it for yourself if you want to. So let's try to analyze the test cases that we are given over here. Let's see the first one. For example, the number of nodes are 5. There is an edge between 1 and 2, an edge between 1 and 3, and 2 and 4, and 2 and 5. So we are also given the a values. Anyway, let's proceed to the queries. The first query is 1 to 4. In the path that is between 1 to 4, we have 3 nodes, 1, 2 and 4, and the product of the ai values will be 2 into 6 into 3, right? 2 into 6 into 3, which is 36. 36 can be written as 2 square into 3 square, right? And the number of factors of 36 are going to be 2 plus 1, which is 3, into 2 plus 1, which is 3, and which means 9, right? So in the second test case, in the second query, we need to go from 2 to 2, which means it will contain of only one number, which is 6, and the number of factors of 6 can be written as 6 can be written as 2 into 3, which is 2 power 1 into 3 power 1. So the number of factors are going to be 1 plus 1, which is 2, into 1 plus 1, which is 2. That means 4, right? So this is how the situation is going to look like. Now we need to make an important observation here before proceeding further. If we see the number of different nodes that can lie on one path will be of the order big of n, right? It's possible that all n nodes lie on a path. For example, if the tree was a chain and we were asked to find the answer for the path between one leaf to the another, right? Now as we can have different big of n different nodes, their product can be really large. like if we observe, the value of n can be up to 10 raised to power 5 and the AI values can be up to 10 raised to power 6. So it gives us the product as 10 raised to power 6 raised to power 10 raised to power 5. We can't really store, such big numbers. We can, but that is going to take a lot of time if we proceed further in such manner that we find the product and then we find the a number of factors. That is simply not something we want. So instead, what we can do is we can maintain the count of the prime numbers that divide that particular number. For example, in the first query, the numbers that were involved were 2, 6 and 3, right? We know that the prime factorization of 2 is just 2 power 1, and for 3 it's 3 power 1, and for 6 it's 2 power 1, 3 power 1, and their product is going to be 2 power 2, 2 raised to power 2 and 3 raised to power 2. So if we know that if a number is of the type p1 raised to power alpha 1, p2 raised to power alpha 1 and pk raised to power alpha k, where p1, p2 up to pk are different prime numbers and alpha 1, alpha 2 are their pars, so the number of divisors in this case are going to be alpha 1 plus 1 into alpha 2 plus 1 up to alpha k plus 1, right? So we need to come up with something where we are able to store the number of different primes and their pars in the current product. Now for the smallest query, what can basically be done is that for every query, we can find the path in big O of n by simply doing a DFS or a BFS, and then we can basically traverse that path and make a note of all the different prime numbers and their pars, and then we can basically print the answer. Let's try to analyze the time complexity of the method that I just told you. If I talk about just one query, we'll be having two nodes u and v, and the first thing that we need to do is find the path between these nodes, right? That is going to take big O of n. Then we'll have to spend some extra time in finding the answer. Let's say that the path consists of L nodes, and if we are to just take the extreme case, this L can be up to n, the maximum value of this L can be n, and then let's say the nodes that I just found to be lying on the path have the AI values as let's say AI1, AI2 and AIL, right? I need to process these numbers to find their answer, find their products number of factors. To do so, what I'll be doing according to the variable, according to the method that I just told, I'll be initializing my answer by 1. I'll be visiting each number one by one, and I'll add the prime factors pars of all of these numbers to some data structure, so that I have a note of the par of each prime factor, and then I'll basically add their pars plus 1. Not exactly add, I'll get the product of their pars plus 1, and my answer will be that answer. So to store the pars of the prime numbers, what can be done is I can have a map of int and int, and then I'll basically be iterating on its prime numbers, and will be adding the pars of its prime factors to my map. Then for this one, and so on, then I'll be iterating on this map, and I'll update my answer. For example, if I'm to give an example, we had for the first query, which was 1 to 4, the numbers that I got were 2, 6 and 3, right? Let's say I have my count, the map, and when I start iterating, after the first iteration my count of 2 becomes 1. After the second iteration my count of 2 becomes 2, because then I would have added the count of I would have added to count of 2 one more, because 6 is 2 power 1, 3 power 1, and my count of 3 is going to be 1. And after this iteration, after having visited the whole array, my count of 2 is going to be 2, and count of 3 is also going to be 2. So in this manner, in the extreme case, what will be the time complexity? Let's try and see. For each number I'll be iterating, so the time complexity is going to be big of n in extreme case into the time that I'll need to basically process that particular number, and the time that I'll need will be proportional to the number of prime factors that it has, right? Because I'll have to iterate over its prime factors and add the power of each of them to the count. And even let's say my this count is not a map and it's a array, and we'll ignore the log n factor, so I'll need big O of prime numbers time more, and the prime factors, the maximum number of prime factors can be up to 10 only, right? So in all, the maximum time that it can take for a query will be of the order 10 raised to power 4 for this case. So it will work, right? This brute force method will work. Anyway, let's not just talk about the smaller subtask now. I'll be moving on to the largest subtask, the original problem, in which n and q both can be up to 10 raised to power 5. So I'll be explaining the method that I used. There will be a bunch of things that you'll have to read. I'll give the resources as and when required, and I'll be trying to explain the method in an efficient manner. There were a lot of optimizations that had to be done even after using that particular method, like changing all of the maps to arrays, and making sure that there is no extra traversal, removing every log n factor that I could, and so on. After doing all that, I managed to pass it. Before proceeding further, you'll need to read about what Mohs algorithm is. This is basically an algorithm which helps us to reduce the time complexity by reordering the queries, by reordering the way in which we answer the queries. So this is an algorithm for arrays in which we have L to R type of queries. Since it is a tree, there is something extra that we need to do in order to use this algorithm, and so for that you will have to read something that explains how to use Mohs algorithm for trees. I'll be giving you the link to an article. The article is this one, Mohs algorithm on trees. It explains in a beautiful manner how we can basically use it to handle path queries, because the queries that we have here are path queries only. And before that, you will also have to read this article if you do not know about even Mohs algorithm, right? I'll be using the piece of code that is given here at the end of this article, so go through this as well once and try to understand it, how it works. So we'll proceed to the code now. I'll be explaining what all I have done line by line, and what all optimizations did I do, and how did I manage to remove all the log factors and the things I was talking about, right? So the first thing that I've done is pre-computation, the computing some values that I'm going to need during my test cases, and I just did it for one time because I'll be needing them in all 3 test cases, and I don't want to do these things 3 times. So these are the inverse values, in the inverse modulo values. This is a somewhat unconventional way to do it, is an unconventional way to calculate the mod inverse values. So this is something I read on cpalgorithms.com. I'll give down the link to that article as well. You can read there that how this thing works, because in general we either use an extended Euclidean algorithm, or we basically get the number n raised to power mod minus 2 to get the inverse value if mod is prime, but that both of them are going to take an extra log n factor, and I don't want it to take that extra time, so I use this. Also, regarding the range, if you notice that the range that I have used, the range of the numbers that I've calculated the inverse values for, are from 1 to 20 times max n. Max n is basically 10 raised to power 5 plus 5. This is because the maximum value for the number of cities can be up to 10 raised to power 5. So this is because the inverse values are needed for the powers of prime, and the maximum value that I can need is the power of a prime. And let's try to calculate what is the maximum power that a prime number can have in a path. So the maximum prime power that a single number can have is 20. We know that the numbers are less than or equal to 10 raised to power 6, so the power at max can be 20 in case the number is 2 raised to power 20, right? So also we know that the maximum number of numbers that can be there on a single path are up to n, so of the order 10 raised to power 5. And let's say if each number was 2 raised to power 20 only, so the number of the power of 2 at max can be up to 2 into 20 into 10 raised to power 5. So I've calculated the powers up to 20 into 10 raised to power 5 plus 5 to have some extra values. So after doing this, I have calculated the prime factorizations for each number from 2 to 10 raised to power 6, because the range for the AI values was up to 10 raised to power 6. Now let's see how this loop works. This array PRM is basically of the type vector of pair, and I'm using vector of pair instead of map to save some time again. This vector of pair will give me the prime factorization of each number from 1 to 10 raised to power 6, right? Now I'm starting my iteration from 2, and if PRM I dot size is greater than 0, it means that it has some factors that are less than this number. It means that this number is not prime, so I'll just continue. Else, if this number is prime, I am using this method to calculate the power of I in each number that is greater than or equal to I. So I have initialized my k with I, then I am doing it while k is less than or equal to 10 raised to power 6, and during each iteration I am initializing my j by k, and I'm adding k to j and doing this until j is less than or equal to 10 raised to power 6. And if k equals I, it means that this is the first iteration. I'm in the first iteration because after every iteration I'm multiplying k with I. So I'll need to push back I and 1, because the number of the power of I is going to be 1 at this particular point. Else, if I am at the second or some other iteration, then I'll just increment the counter at the back by 1. Let's take an example to understand how this works. Let's say the value of this n, the 10 raised to power 6, was instead 10. The numbers that we would have had would have been 2 to 10 in that case. Let's analyze it for the case when I equals to 2. When I equals to 2, I initially my k value is 2, so I'll iterate. When k value is 2, I'll iterate with 2, 4, 6, 8, 10. So 2, 4, 6, 8, 10, and for each of the value, the we would push back to PRM of j I comma 1. So the first value will be I, and the second values will be 1, 1, 1, and 1 respectively. Then I'll multiply my k with I, so k will become 4 now. After in the second iteration, I'll be iterating 4 onwards, so this will become 2 and this will become 2, and in third iteration this 4 will become 8. Then I'll be iterating 8 onwards, and this the value of this value at this 8 will become 3. So if we see that the power of 2 in 2, 6 and 10 is 1, and in 4 it's 2, and in 8 it's 3, so it's exactly what we require it to be. So this is how it works. Now after having done the pre-computations, I'll start taking the processing the test cases. I take the number of test cases as input, and this WT works because I have defined it as where is it? Yeah, WX, NTX, CNX, and whilex minus, right? So I'll input the number of cities, then I'll clear the adjacency lists from the previous test case, because I don't want the edges of those test cases to mingle with the current test cases edges. So then I'll input the n-1 edges u, v, and I'll push u to the v's list and v to the u's list, and then I'll input the error values, which are these in this case. Then I'll basically be flattening the tree. I'll be converting it to the 2D to the array that will basically correspond to the LR queries, and to do that I'll assign the appropriate values. This current is going to be the timer that you must have saw in the article in which they told how to use Moore's algorithm for trees. And we'll be doing the DFS in the same order, in the same manner that was specified in the article. So L is basically corresponding to start. L of u is equals to plus current. Then flat of current is u. Flat is basically the flattened tree. And then I am updating this parent values. These are something that will be used for calculating the LCA. In this, the pair of I u basically represents the 2 raised to power ith parent of u, right? These will be used in calculating the LCA in an efficient manner. The method that will be used here is called binary lifting. You can read about that as well. You can just Google it out, or I'll also mention a link in the video description. So after having done this, we'll simply call the DFS further, and before doing that, we'll update the level value of the current child and the parent value, the first parent's value of the child as u, and then the r of u will be assigned because we have completed the u subtree, and flat of current will be again u. We can just dry run it for this case. For this tree, the tree is 1 2 3 4 and 5. So initially when I'll call the DFS, my use value will be 1, so I'll push to the flat array 1, then I'll come here 2, then 4, then again after having done the DFS for 4, because I wouldn't have found anything in its subtree, then again 4, then we'll go back to 2, and I still have 3 left, so 3, then again, sorry, it's not 3, it's 5, so again 5 because there's nothing in the subtree of 5, then again 2 because we have visited the subtree of 2, then we'll come back here, then we'll move to 3 because 3 is still left, then again 3 because there is nothing in subtree of 3, then 1 because the subtree of 1 has been visited completely, right? Now we'll have the corresponding L and R values as well, which will tell me that what is the index of the first occurrence of a particular node and what is the index of second occurrence of a particular node. For example, we know that the number of nodes that we have here are 10, then the L of 1 value will be 1 and the R of 1 value will be 10, I think. 1 2 3 4 5 6 7 8 9 10, yes. And similarly for 2, it's going to be L of 2 equals to 2 and R of 2 is equal to, I think, 7. 1 2 3 4 5 6 7, yes. So similarly we'll have the L and R values for rest of the nodes as well. Yeah, so after having done the DFS, yeah, then now I am assigning the block numbers to each index. I am the BL num I will basically represent the block number that the ith index lies in, and before that the block size is going to be square root of current, right? Because by this point we know that current will represent the size of the flattened array. It will be 2n, we know, but let's just use current for simplicity. Now we know that, let's say the size is s, then the indices 1 to s will lie in the first block, s plus 1 to 2s in the second block, and so on. And we see that the value of this I by s for this, sorry, I minus 1 by s for this first block from 1 to s is going to be 0, right? Because I minus 1 values are going to be 0, 1 up to 2s minus 1, and if I add 1 to each of them, then the block number is going to be 1. So this is something that will be that will be satisfied by this formula. And similarly for the second block, the I minus 1 values are going to be s, s plus 1 and 2s minus 1. So I by s is going to be 1 for all of these, and if I add 1, then the block number is going to be 2, and so on for next blocks. Then I'll take as input the number of queries, then I'll process each query. So to do that, not exactly process, take input and set some values for further processing. UV are the nodes, are the pair of nodes that represent the current query. Then I'll calculate the LCA using the manual lifting method. You will read that in the article, and I'll also be linking down the code so you can have a look. So after having calculated the LCA, I just made the L value of U smaller to avoid writing more code, because then I would have to, if I don't do this, I would have to take care of both the cases. So by this point I'll know that U has a smaller L value, so I'll write the code accordingly. Now if the LCA value is U, then as you must have seen in the Codeforces article, the L value and the R values will be L of U, which is start of U, and start of V, with the name that I have used in the code is L. So else the L and R values will be end of U to start of V. But note that in this case we'll also have to add one more node, that which is I think start of U, to our answer. We would have to consider the contribution of that index as well. This is why I am storing the LCA value for now, because while processing the queries I'll know if the LCA is not equals to the U, then I'll basically add the contribution of that particular node as well to the answer. And now I am storing the index values because I'll need to output the answer in the same order only, and I'll be sorting the queries, so I need the ID as well, the ID value as well, right? Then I'll sort the queries according to the Mohs algorithm's comparator, which is first sorting according to the block number, and if the block number is same, then according to the right values. There is one more optimization that I read somewhere, and I applied that as well, which is if the block number of the current index of the L value of the current query is odd, then I'll sort it in the increasing order, otherwise in the decreasing order. I think it may work if you just sorted according to the standard Mohs algorithm, but I just did it to lower the time by some more milliseconds. So after having sorted, I'll move on to the compute function, which performs the standard Mohs algorithm and basically gets us the answer for each query. A large chunk of this compute function has been taken from the Codeforces block only, the code which was given at the end of that article, as I just told you. So these are the current L and the current R values that are to be set initially, and they'll update themselves according to each query's L and R values. This is the current answer. This is 1 because we haven't included any number in our current range, our path initially. So these are basically two arrays that I require to store something for each range. This current PRM count basically represents the powers of primes that I have for each prime in the current path. For example, if my current path consists of numbers 2, 6 and 3, 2, 6 and 3, I am talking about the case when the path was 1 to 4. So I'll have current PRM count, let's say C of 2 equals to 2, because the power is 1 in 2 and the power is 1 again in 6, and C of 3 as well equal to 2 because the power is 1 in 3 and 1 in 6, and all of the other values are going to be 0. And the current answer is going to be 2 plus 1 into 2 plus 1, which is 9. So the current answer will basically contain the answer for the current range. This change array is basically going to contain that how much is some number going to contribute when I am going to move from one query to the just next query. We'll see what this does in detail in some more time. So this is a vector to do, which will also be clear what it does in some more time. I am just clearing it so that the values from the previous test case don't interfere with this test case. And this viz array basically will tell me that have I visited this current index or not, because if you remember, in in a path, in the L2R array of a path, I should only include those elements in my answer which occur exactly once. So this will basically tell me that if I have already visited them or not. If I have not already visited a particular index and I am visiting it now and I'm including it now, it means that it has to be included in the answer. But if I would have already included the current index, the current node in my answer, and I'm visiting it again and I'm including it to my current range, it means that particular node is present twice in the current range. So I'll make it 0 gain to ensure that I am not including it to my answer. We'll see soon. So this is the loop from 0 to m, and this all is standard algorithm, and this include or exclude function is something that you should have a look at. Yeah, so in this include function, what I'm doing is I have an index and I have a change array which will be updated, and this to do is made as global only. And this to do, I'll push arri to the to do vector. It means that this arri is something, this number is something that we have to consider while updating our answer, because the numbers that do not enter in, do not that aren't in this to do vector are not to aren't needed to be considered while calculating the answer for the current range, while transiting from the previous answer to the current answer, right? So I'll just store the error values that are needed to be checked, that are needed to be included or excluded from the last answer to get the current answer. Now if this ith index, this index I, is already in the range, this I is basically node number. If you see, then the current L and current R are basically the indices in the flattened array, and this flat of current L and the flat of current R are going to give me the node numbers that these indices represent, and then I'll have the error I value from the node number. And if that particular node has already been visited, if it is present in the current answer, if it is contributing to the current answer, then I'll exclude it, because I do not want to include it further, because now the number, the node I has been counted twice, because it is present in the current range twice. So I don't have to include it now. So I'll just do change minus minus, because I have to exclude the current number, which is error I, once more, right? Let's say there were, the range that we are talking about had, let's say, 4 nodes, okay, 4, 4, 3 and 1. So, and my current range is nothing, right? I am including the numbers one by one in the current range, say for example. Now if when I visit this 4 for the first time, and let's say the error values for these are a of 1 equals to 5, and a of 3 also equals to 5, and a of 4 equals to, let's say, 2, right? When I'm when I'm visiting this 4 for the first time, that means my vis of 4 will be 0. I'll include this to my answer. This 2 will be pushed back to the to-do list, and this change of 4, the change of 2 will be incremented by 1. Now the change of 2 will be 1, and then when I'm visiting it again, then I know that it has already been visited. So I'll just do change of error I minus minus. Now the change of 2 will be 0 again, right? Because it has been visited, because the index 4 has been visited twice. The node number 4 has been visited twice. Then I'll move to 3. It hasn't been visited yet, say for example, and I know that I have to include it. So the value at 3 is 5. So I'll do C5 plus plus, which is, it will become 1 now, because it has to be included once now. Then I'm again visiting 1. The node 1 hasn't been visited, so, and the value at the value at 1 is 5. So C of 5 will become 2, because I have to include 5 2 times now, because earlier I had to only include 5 in my answer. Now I have to include 5 square, because 5 will be multiplied twice. So this is basically going to give us the power of the current number that has to be added to the current answer, right? That has to be multiplied with the current answer. Yeah, so if visited of I, then just do minus minus. If not visited, then do plus plus, and just take XOR of viz of I by 1, so that if it was 0 initially, then it will become 1. If it was 1, then it will become 0, right? Now after having done this, after having set the current range to L and R of the current query, I'll just get the node values, the current L and the current R. The current L will give us U and the current R value will give us V. Now if the LCA is not equal to U, you would have seen this in this article that I gave you, that if it is not equal to U, then one more index has to be added, which is the LCA. One more node has to be added, which is the LCA. Then I'll include it as well. Then I'll calculate the answer, then I'll make the changes. Then I'll we'll just see how to make the changes in the answer. So after having made the changes, I'll just clear the to do, because it will be used in the next query as well, so I don't want it to mingle with that. And I'll set the answer of q of I.id as the current answer. And if it's not equals to U, if the LC is not equals to U, then I would have included this extra node, or maybe excluded. I'll just again take the complement. If it was included, then I'll exclude it. If it was excluded, then I'll include it, right? So after having processed all the queries, I'll just print all the answers. Now let's see what is being done in this loop. Now I am iterating in my to-do vector. If the change of A, then now this A values will represent the original numbers, the numbers that I need to multiply, and not the node numbers or the indices, because we added ARR I to the to-do list and not I. It is possible that several values are entered in the to-do list multiple times, but we'll ensure that only the values corresponding to the indices that need to be updated for the current query are only entered. There are no redundant values. They are it does not contain a lot many number of values. It just contains the values that we really need to check for. Yeah, so while iterating, if the change value is 0, that means we don't have to really do anything. We have to just multiply the current answer by a raised to power 0, which means that the current answer will basically remain same. Else, if it's not the case, then I'll go to the prime factorization of the current number A for auto IT belonging to PRM of A. We just saw that in the pre-computation function we calculated the prime factorization for every number, right? So let's move back. Yeah, so we'll iterate the prime factorization. The prime will be it.ff, and its power will be it.ss. ff and ss are defined as first and second. Now I'll divide the current answer by previous power of p, that is stored in the current PRM count, because it stored the answer for the previous range. I'll divide it by the previous range, the previous power plus 1, which means I'll multiply current by the inverse of that number, inverse of current PRM count of p plus 1, and then take basically percent equals to mod, then make the change. I'll basically add to my current power of p change of a times the power, right? Now say for example, if I am to if I am to multiply my answer with a raised to power change of a, that means the powers of the prime will be added. Let's say this was p1 power 2 into p2 power 5, let's say, and this a value was p1 raised to power 3, and the change of a was, let's say, 5. So it means if I power 5, then it is going to be 15. I'll need to add 15 to this 2 to get the new PRM count. So I am adding change of a into power, which is change of a was 5 and power was 3. I am adding 15 to the previous count to get 17, and after making the change, I'll multiply the current answer by the new power of p plus 1 and take the percent mod as well. Now at this point I'm doing change of a equals to 0. This is because I don't want the change of a to mingle with the next queries, with the further queries. And basically as we just saw, it is possible that some numbers are present twice or more times in the to-do list, but I don't have to make the changes more than once. For example, we just saw that if something is 4413 and a of 1 equals to a of 3 equals to 5, so I'll have 5 two times in my to-do list, and change of 5 is going to be 2. We just saw a couple of minutes ago, right? So if I do not do this change of a equals to 0, I'll add 5 square, I'll multiply the answer by 5 square when I see 5 for the first time, then I'll do it again when I see it for the second time. So it's important to make the change value 0 so that the changes are only made once. Now after having doing it, I'll just print the answers, right? I hope it is somewhat clear. I'll go through the code quickly once again to give you an overall view of what is being done in each function. So first make the pre-computation. In pre-computation I'll be calculating the mod inverse values and the prime factorizations for each numbers. Then take input the number of test cases, then n, then the other inputs, and clearing out the values from the last test case. Then DFS to basically flatten the tree to get the LR type queries to apply the Mohs algorithm. Then divide each divide the indices into blocks, store the block number for each index because it will be used during sorting, right? So then get the queries u and v values, store the LCA because we know that there will be two possible cases for the LR value, the subarray that this particular query corresponds to in the flattened tree. In case if LCA equals to u, there will be different case. If the LCA is not equals to u, then there will be a different case. So this will use binary lifting. The link is in the description. You can read about binary lifting on by clicking on that link. Then if L of u is greater than L of v, I'm swapping it to avoid writing some extra code, because at this point onwards I know that L of u will be less than L of v only. Then setting the ranges and the ID values, and sorting the queries according to the Mohs algorithm, and then computing the answer for each query. The current L and current R values will be assigned to something. As you can see, this current range does not contain any value because L is greater than R, right? The current answer is 1 because it basically does not contain any number. So when I'm multiplying it by something or dividing it by something, it shouldn't contribute to it. So I have set it as 1 initially. Then I have current PRM count and change. This change will basically tell me the contribution of each ARRI of each different number that will happen while transitioning from one query's answer to the next query's answer, right? And this current PRM count will tell me the power of each prime number that is present in the product of the numbers in the current range, right? Then this to do vector is to tell me about the values, the ARI values, which I'll need to check whose contribution I'll need to include or maybe exclude for the next particular query's answer. And this viz array will tell me that whether I have to exclude the current number, the current node, or include, because it will tell me that if is the current number present in the is the current node present in the range once or twice or not even one time. So it will be 0 if it is not even present one time, or it's present twice. It will be 1 if it's present one time, right? If it's present basically exactly once. Now I'm iterating the queries in the sorted order, the order of according to the Mohs algorithm. Then I am setting my current L and current R to the L and R of the values. This is something that you would have seen, you would have learned when you would have seen the Mohs algorithm and the Mohs algorithm on trees article. Then this include or exclude basically sees if the current node, if it's already present, then I will have to reduce its contribution by 1, I would have to exclude it once from the current answer, because now we have seen it twice, right? So change of error I minus minus. Else if it's not already in the range, then I'll just add 1 to the error i's contribution, because according to the node I, it should contribute once more, right? Then visited I will be set to 1 minus visited I, or I'll simply XOR it by 1. Then I'll see if that extra node has to be included in the current range or not, by checking if the LC is equal to, if the LC is not equals to U, then I have to include one extra node, and I'll delete the contribution of that one extra node from the answer after updating the answer. Now to update the answer, I'll iterate on the to do, because this will contain all the error I values which can possibly contribute to the change from the last answer to the answer that I'll have after processing this iterations, after processing this loop. Then if change of a is 0, that means that there is no contribution finally of the current array, of the current number, sorry. If yes, if it's not 0, if there is a contribution, then I'll iterate in its prime factors to then the p will be the prime factor and pw will be its power. I'll divide it by the previous power plus 1. I'll make the change, then I'll multiply it by the new power of plus 1. It means basically let's say the power of 2 that was in the current answer initially was 5, and afterwards it's 2 raised to power 1, say for example. Then I'll simply divide it by answer by equal to 6, and because the contribution of this power in the answer was 5 plus 1, and then I'll say answer into equals to 2. But in between I'll also update the powers, so the power has to decrease by 4, right? Yeah, so after having done it, I'll just clear the to do for the next query and assign the answer. And if as I just told, that if that extra node was included, just exclude it, then I'll print the answers for each of the query, right? Now the time complexity in general for this algorithm is big of n root n, but in this case it's going to be big of n root n log n, because the simple if it would have been in a simple manner, it would have been n root n, but while making the changes, I have this loop of extra log n factor which contains basically the prime factors of the current number, so it will be of the order big of n root n log n, not exactly log n, log of ai values, right? So I hope the whole thing is clear. If there is a doubt at some point, you can drop down a comment. I'll try to give you either a source to clear it out, or I'll clear it out in the comment section itself. So this was it for this video, guys. Thank you very much. See you guys in the next video.